So in this video, I want to talk about Boolean simplification using Kmaps. Simplification of Boolean function leads to a simpler and usually faster digital circuit. Simplifying Boolean function using identity methods we discussed in the previous lecture are very time consuming and also error prone as well. And sometimes we don't know exactly what is the way to combine the variable together in order to simplify the function. So in this week lecture, we will present an easy and systematic method for reducing Boolean expression. That's 1953, Maurice Carnot was a telecommunication engineer at Bell Labs, and while exploring the new field of digital logic and its application to the desired telephone circuit, he invented a graphical way of visualizing and then simplifying Boolean expression. So this graphical representation, now known as the Kmap or Kmap, is the name of his honor. So basically, Kmap is a metric consisting of rows and columns that represent the output values of a Boolean function. The output values placed in each cell are derived from the minterms of a Boolean function. Okay, so basically a minterm is a product term that contains all of the function variables exactly as one. Okay, keep in mind that all of the variable exactly once, either a complement or not a complemented. Okay. We'll give an example in a minute. Here's an example. The minterm for a function of having inputs x and y are a x0, y0, x0, y, hy0, and hy. Okay, so basically for the two input variable x and y, we will have the four minterms. Okay. Consider Boolean function f of x and y equal to hy or with the hy0. Okay, so its minterm gonna be, because this one have the two variable x and y, so the minterm gonna be 4 and gonna be represented by h0, y0, h0, y, hy0, and hy. Okay, so that's corresponding to the value of x equals 0, y equals 0. So that's gonna h0, y0. H0 y equal 0 1, hy0 1 0, and hy y equal to 1 1 when h equal 1 and y equal 1. Okay, so basically that's the key concept of minterm is that that's the way we combine the input variable together with each other, so that either complement or not complemented. Okay. Now, for the case of three input variables, we have the minterm that are shown on the diagram here. So basically, we have the input variable x, y, z. Now we gonna have a 8 minterm right here, gonna be from h0, y0, z0 to x, y, z. Okay, so we can see the same pattern as with the two variables as before. So h0, y0, z0 corresponding to the value of h, y, z equal to 0 0 0, and go 0 0 1, 0 1 0, and so on to 1 1 1, corresponding to the minterm h, y, z. Okay, so basically for the three input variables x, y, z, we have the 8 minterms. Okay, so the general formulation for computing the number of minterm is that let's consider n is the number of variables, so we have the number of minterm gonna be 2 power n. Okay, so that's the general formulation to compute how many minterm given a number of input variables. So basically, we can see that a Kmap have a cell for each of the minterm. This means that it has a cell for each line for the truth table of a function. Okay, so basically that correspond representation between the truth table and the Kmap. Okay, so let's consider the truth table for the function f of hy equal to hy. Okay, that's shown the right along with its corresponding Kmap right here. So the Boolean function f of hy equal to hy have the truth table right here. Okay, the truth table is going to represent with different value of the inputs x and y, and gonna be represent the outputs of the function f equal x y right here. So with the given function right here, you can see that the output the value of the function f x y equal to 1 only when x equal to y equal to 1. Okay, so this is basically that's the end function of x and y. Okay, so this is truth table of the f of x and y. Now from here you can see that now we can represent using the Kmap. So basically Kmap of two variable x and y, we can represent x corresponding with this column right here, and y gonna be represented by the row right here. Okay, the value right here, that's the possible value of the inputs y, so this can be 0 or 1. This the inputs x also can have the two values 0 or 1. Okay, so when x equals 0, y equals 0, so this cell right here will gonna be corresponding to the input x equals 0, y equals 0. Okay, so the output of the function gonna equal 0. So this cell right here corresponding to the first row of the truth table right here. Okay, now x equals 0, y equals 1. So x equals 0, y equals 1. So that's gonna be the cell right here. So that's corresponding to the second column of the truth table. X equals 1, y equals 0. So that's gonna be this cell right here, correspond to the third row of the truth table, and the last row right here, x equals 1, y equals 1, and the output equals 1. X equals 1, y equals 1, and the output of the value of the function equals 1. So this is corresponding to the last row of the truth table right here. So you can see that actually the Kmap right here is just another different way to represent the truth table of a Boolean function. Okay. So that's the case for the function of f x y equal to x and y. Okay. Now consider the same two variables x and y, but different function. We can see that the Kmap for the function of f x y equals to x or y. That's right here. So here the different function of two variable x and y. So this function f x y equal to x or y. Okay. So we can see that this is the input variable x and y. We can set the four possibility of the input values, and with x or y, you can see that if x equals 0, y equals 0, we can see that the x or y equals 0. On the other cases, x equals 0, or y equals 1, or x equals 1, y equals 0, or both of them equal to 1, we can see that the value of the function equals to 1. So we can see that with this function, we also can so basically you can see that this function right here is just equivalent to the OR of the all minterm that have the value of 1, right? And basically we can see that this truth table right here can be represented in the Kmap, where the first term right here, x equals 0, y equals 0, we have the first cell right here corresponding to the first row of the truth table right here, that's 0, and all the other term right here corresponding to different value of the inputs, 0, 1, 0, 1, that's the second row right here, this is the third row, and this one the last row in the truth table. Okay, so basically you can see that we also have a different way to represent by adding all the minterm in the Kmap right here, where the value equal to 1. Okay, so we can see that f x y can be equal x plus y, so that the given form. And now by using by representing in the Kmap representation, you can also represent in different way by adding all the minterm together. So you can have the first one right here corresponding with the x naught y. So this is the first term right here corresponding to this value 1. The second term right here corresponding to this one, just x y naught. Okay, because x equals to 1 and y equals 0, so that's that cell right here gonna be x y naught, and the last cell right here, x equals to 1, y equals to 1, so we could have the represented by x and y. Okay, so basically that the some basic information about the Kmap, and the next video I'm gonna talk about how to use the Kmap rules to for simplification of the Boolean function. Okay.